Okay, welcome everyone to my seventh lecture on quantum topology without topology. Today we kind of want to connect what we have seen so far, or we start connecting what we have seen so far. So last time I did a little bit of homological algebra or linear algebra in categories, like additive categories, linear categories, abelian categories. And before, so for the first 5 lectures, the flavor was a little bit different, right? So the first 5 lectures was more like some categorical version of topology in the end. And well, for the next 4 lectures, so for the rest of the lecture series, we kind of want to connect both together. And then you have really a lot of structure to play around with, and you can actually prove a lot of really nice theorems. And in the end, you will be able to answer the main question, which was how to construct those nice functors from diagrammatic categories to some linear algebra-like categories. And not just how to construct them, that's the next question, of course, but also how to construct target categories. And yeah, what I'm going to explain today is basically we want to connect abelian and additive structures with rigid, so dualities and pivotal structures. So let's see how that actually works. So in some sense, I want to explain what are suitable categorifications of algebras and rings. In what sense? Well, I already basically explained that there are natural categorifications of rings, of monoids, which are monoidal categories. And there are kind of natural categorification of modules or vector spaces or whatever, which are kind of linear categories or additive categories or abelian categories, whatever. And so they categorify abelian groups, right? So that's basically what I tried to explain last time. And why not bring both together? Then you have an addition, because you categorify abelian groups. And you have a multiplication, because you categorify kind of a monoidal structure. So you found a categorification of a ring. And that's what I'm going to explain. Okay, so let's just jump right into it, right? So we will have from now on categories for several structures, of course. So as I just said, right, we have monoidal structures, we have additive structures, we have various flavors of those, and we kind of stack them all together. So whenever you see something like this here, this would mean it's rigid, it's k-linear, and it's abelian. So I try to put the topological things in the front and the linear algebra-like things as subscripts. We will see. So that's what I say here. So rigid is kind of a topological property. Remember, that was something like you have cups and caps in one way or the other, and k-linear and abelian are, of course, very linear. Well, k-linear already has it in, but it already sounds like it's linear, right? K-linear and abelian is, of course, linear algebra-like properties. Yeah, and I will use several shorthand notations, which I'm going to explain throughout the text. Don't worry about it too much. But let's just jump right into it. And one of the crucial things I want to explain is, well, we kind of, first of all, we need a bigger class of certain categories. And we had this nice envelopes, right? We had a k-linear envelope, a k-linear extension, whatever you want to call it, additive envelope or additive extension. Same for abelian. Abelian wasn't all that nice. Additive on k-linear was pretty good. And there's something in between, but I'm going to explain right now. But let me start with some motivation. And of course, if I start with motivation, so I said again, I want something in between additive and abelian, basically. And whenever I start with motivation, I start with fact k. Right? We're doing linear algebra, right? So yes, let's start with vector spaces. And if you remember, there was this nice diagram when I had some x plus y, which is of course pretty trivial for vector spaces, but let's ignore that. Right? So, and you had a projection to x, and you had a projection to y. So p whatever, px, py, and you had the corresponding inclusions the other way around. Ah, right? So let me just write ex and ey for what? For this direction, okay? Or respectively this direction. The first project that include, and I just write ex and ey. And the point is that everything is, of course, built that the image, it's in a binary category, right? You know what the image is. It's the image in vector spaces. These are matrices, right? Or linear maps, whatever. The image of ex is x, and the image of ey, which is just the identity minus ex, of course it is. Just think about it for a second. The idea is y. Okay, that's not very surprising. That's how it's built. Um, but then come three really crucial properties. One, two, three. One of them, so both work for ex and ey. I'm just doing it for ex. Well, everything is written for ey as well, but anyway. So ex is an idempotent, which just means ex squared is ex. Similarly for ey. Here is just ex times, so this is called an idempotent. And I should put it in blue. Okay. This property is called orthogonality, and it's basically ex, ey is 0 in both directions. And it's a really easy calculation. You just do it. I mean, it's one line. It's trivial algebra. Okay, and then there's another one, which I put in green. It's called completeness. So let me just also order those. So this here is red, and this here is green. And completeness is just saying that ex plus ey is the identity. Okay. So we have three properties. We have idempotence, blue. You have orthogonality, red. And you have completeness, just green. And this is really important. These are the three important properties which we will kind of generalize in a second. Right now, this is just in vector spaces. And you basically just observe that you have a computed diagram of this form where you can write down those matrices. So here's a matrix and here's a matrix. And it basically shows that under this circumstances, Z is isomorphic to the image of Ex and the image of Ey. And how do you see this? Well, you would take those matrices and compose them. So let me just do it for you here, for example. This matrix, Ex and Ey. And there is this other matrix. Let me put it in orange, which is Ex and Ey. And if you compose them in the usual way how you compose matrices, then you will get, what do you get here? Ex squared, very good. You get ex ey, ex ey, ey squared. And by the properties from before, those things die, right? These two sum up to the identity, so this is an isomorphism. And the inverse is just the inverse composition. So first orange, then green. Okay, that's pretty nice. So you have those projections and inclusions give you idempotents which actually decompose Z into the image, into the direct sum of those images. So we get a direct sum decomposition. And yeah, and this is basically an equivalent. I mean, there are two different ways to describe the same problem. And this sounds, if this looks, so this is really powerful. If this looks a little bit silly, Then the point is that there are 2 points. First of all, if you just let's look at it again. So what have I actually used about vector spaces? Almost nothing. No. So this was trivial algebra here. Those three properties, and the trivial algebra gives me this diagram, and this diagram gives isomorphisms by again trivial algebra. So what have I actually used about vector spaces? Well, I have nothing, absolutely nothing. So this should work in any reasonable category, and that's the whole point. Whole point one. So the first important point, and the second important point is so this works. So this is good, good. The second point is okay, this was kind of a silly example because I assumed that z is actually equal to x plus y, right? Um, if nature gives you a problem, then z might be still equal to x plus y, but you don't see it because it's kind of hidden. I will give you an example in a second. And this is kind of a construction to create those direct summons, to find those direct summons. You need to find idempotence, right? Um, so this is the philosophy of idempotence. You need to find idempotence. Idempotence decompose objects into direct sums. The only things you don't want to take are the trivial idempotence because they are kind of stupid, which are usually zero in the identity. You want to find a non-trivial idempotence is equivalent to a decomposition of your objects. Okay? Let me say it again. Non-trivial idempotence equivalent to decomposition of objects into direct sums. Direct sums are easy, so that's what we want. Let me give you an example where this is really not trivial, because in this case, the corresponding z doesn't come as x plus y. So it's a hidden x plus y. Okay, so I take my two algebras here. So A, uh, and the green one B, and they look very similar. It's zx mod x squared, or it's cx mod x squared minus 1. There doesn't seem to be a huge difference between them. So let's have a look. Actually, they're wildly different. They're really, really different. And the idempotence is telling why. Okay, and it's a very silly calculation. It's easy. So every element is, of course, of this form, right? A plus bx. Why? Because you have killed everything of power x or bigger, or you can actually replace it by something different. So any element is determined by those two numbers a and b. And you only do the following calculation. It's an almost trivial calculation. You square this thing and you get two different cases depending whether you're in A or in B. And they look very similar. It's an equation you need to solve in A and B. And the equation you want to solve is this one. And you want to find idempotence. So you want to solve this equation. So you want to find A and B such that this equation works. And you will try this in A. So you just in A. So this was this purple like thing. In A, you want this to be satisfied, right? So, or rather, this one, of course. So we do it this way. This thing here should be this one because this thing by definition is this one. And you try to solve that and you find, oh, I only have the trivial solutions. Okay, the trivial solution means, well, you only find two idempotents, zero and the identity. And this already tells you that the thing is indecomposable. Okay, these are the only idempotents you find. There are no others. Okay. So there is no non-trivial decomposition of A. For B, the equation looks very similar. So my green one. But you can actually solve it. Here's the solution. Okay, so it's not so hard. So you have a plus idempotent, you have a minus idempotent, and they are basically the roots of this polynomial x squared minus 1. Yeah, because, well, plus and minus, right? Plus and minus 1. And if you just multiply them, you will see that they exactly satisfy those three equations we want to be satisfied. And This just means that you get an idempotent decomposition. This decomposes further, and here you go. Cx mod x squared minus 1, blah, 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 is actually isomorphic to c plus c. So they're wildly different algebras. Also, they look very similar. They look very, very, very similar, but they're wildly different algebras. And the way to see this, in this example, is to use just idempotence. It's a calculation to check whether you have idempotence. I mean, that's just almost trivial linear algebra, or algebra, not linear algebra. Just solving certain equations. That wasn't all that bad, right? And this is how you should think about it. In life, almost nothing comes as decomposed as a direct sum. So you need to find this decomposition. And that's why you need this philosophy of idempotence. What you really need to find are idempotence. Okay, so idempotence, cool, right? Idempotence, good. E squared equals E, that's the thing we like, right? So let's formalize this, okay? And the way to formalize it is called the idempotent closure. It's exactly like the linear closure or an additive closure or a Abelian closure or envelope or whatever I called it. It doesn't matter. But you basically want to have idempotence and let's have a look here, images of idempotence. So in the Abelian category, you always have images of everything. But what I tried to explain last time is a little bit like Abelian categories. They might be a little bit rare. Additive categories are everywhere, but Abelian categories are a little bit rare. They're nicer, but rare. And they have images for everything, but maybe that's too much. So maybe we only need images for idempotence because we want to play the game that I just explained. And that's exactly what the idempotent closure does. So the idempotent closure of a category, of any category actually, really of any. So the notion, why? Well, this notion makes sense in for any category. So for any, and we can always compose, so this is a morphism. So we can always ask whether this equation is true for any C. So you can write down the idempotent closure for any category, and I denote it by this funny symbol here. And it's very easy definition. So objects are now just pairs of X and an idempotent on X. That's it. So for each object, you also choose an idempotent. Okay? And all idempotent. And the tricky part will be to find the objects, basically, to find all idempotents. Okay. So objects are colorings of old objects with idempotents, if you want to think of it like this. And you have a compatibility condition for morphisms. It's exactly what you think it should be. So if your objects are those guys, X with an idempotent or Y with an idempotent, and you have two morphisms, which are still morphisms in your old category, then you want the corresponding diagram to compute. To commute. You also want to compute those diagrams, but you want them to commute. And since you have built everything out of C, it's really easy to see that the thing is a category. Right? Composition is composition in C, so identity is so there's always on each so identities are just the idempotents on xe, the corresponding E is the idempotent, and composition is composition in C, because everything is built from C. It's just the coloring of objects of C with idempotents. Yeah, and it has some nice properties. So let's just discuss the properties. And yeah, whatever. So it's a category. Okay, yeah. It's built to be a category, so don't worry about it too much. The category itself is actually a subcategory. So there exists a fully faithful functor, and it's very silly. It takes every object and sends it to the trivial coloring of the object. Okay? So you always have the trivial idempotent identity, and you can always color everything with the trivial idempotent. Okay. Okay, that's already not too bad. That was the same for the other envelopes as well, right? So this is good. Mm, And the fun fact is, every idempotent has an image in uh, the idempotent completion. So in the idempotent completion, you could speak about images of, well, of idempotents. And the other properties are a little bit, well, okay, yeah. Um, if you do it twice, you haven't done anything. That's why it's called a completion, right? Complete it once more and nothing happens. And the last one is crucial. It looks very innocent, but remember, it was not true or not so easy or whatever for a billion things. But here's good. So if your category is already linear, then your category is already linear. If your category is already additive, then oh, sorry, then whatever. The idempotent completion has the same structure for linear, for additive, for monoidal, for rigid, pivotal, for braided, for everything. So it preserves structure, and that's good, right? Remember, that's what we want to have. We kind of want to remember from the additive closure. It was like, okay, you now have direct sums of objects, but not much has changed. And here, not much has changed either. You now have colorings of objects with idempotence, and you preserve all structure. So this is awesome. This is an awesome property of the Caribbean of the additive closure. Sorry, idempotent completion. Okay. Of course I skipped the proof. It's not very exciting. And because it's a completion, you call something idempotent complete if it's its own idempotent completion, right? So that just means all idempotents have images. And yeah. Um, and actually, the first examples you would write down, they're all idempotent complete. So vector spaces are idempotent complete, module categories are idempotent complete, um, G-graded vector spaces are idempotent complete. But the point is the next example. Uh, Diagrammatic categories are usually never idempotent complete. Okay, and the idempotent completion is idempotent complete. Whoa, what a surprise! But it's usually not a billion. So let's discuss how idempotent completion looks like. For example, in the diagrammatic categories, there was a symmetric group category where I was allowed to draw those symmetric group picture-like diagrams. Remember? And um, and it was easy to make it whatever q-linear and additive and whatever. That was a harmless thing. But you can also make it idempotent complete without any problems, and you can write down idempotence explicitly. For example, I would like you to do this calculation here that you get those two idempotents. Okay, I again call them e plus and e minus, and they are given by those pictures. Remember that you can add pictures, and well, you can multiply pictures by scalars in the usual sense, because now it's q-linear and additive. And I want it to be q-linear because I want to divide. I don't need it to be q-linear. I only want to be able to divide by 1/2. So let's say it's q-linear. And what you then get in the idempotent completion is, so you have those idempotents e plus and e minus, and you get that two dots are actually isomorphic to the image of E plus and the image of E minus. And if you want to think of this in diagrammatic terms, then this just really means now you have your strands and you can color everything with idempotence, right? You have two idempotents, gives them some color. So E plus, for example, you can say it's green, and you can say E minus is dotted and red. And this is then how your decomposition would look like in diagrams. You could decompose two strands further into two objects. I'm a little bit sloppy here, so I'm writing two identity strands instead of two dots. Right? Remember, two dots I could write. So I have two dots, and I just write two identity strands because it's kind of nicer. And this would be isomorphic to exactly what is written up here, and this is how it looks like by definition, or by the property. All right. And what I would really like to keep in mind is idempotent completion is coloring things with idempotence, right? And I just sometimes I really like to draw to color diagrams, like in diagrammatic calculus. And the point is, and this is already what it kind of shows, uh, so that it's kind of a weaker notion. Oh no, I should have done this. It's kind of a weaker notion of abelian. So abelian implies idempotent complete because everything is an image, but idempotent complete usually doesn't imply abelian. So here is a nice example of an idempotent complete category, which is not abelian, and that's really great. I mean, abelian envelopes are hard. Additive envelopes, K-linear envelopes are okay, and idempotent completion is also okay. So this is as close as it gets to being able to do some homological algebra with diagram categories without doing some more complicated yoga. So this is kind of the easiest thing you can imagine. Just coloring things was important. So let me say it again because it's important. So take diagrams. First, allow scalars, linear extension, allow direct sums, additive extension, and now allow colorings of diagrams with idempotence. Uh, idempotent completion. And the only difficulty is to find those idempotents usually. You reduce everything, all difficulties to finding idempotents, which is sometimes a very hard task, but at least it's something you could try. Okay, and before we move on, let me just say, so remember this was kind of so simple here for what we just discussed. These are really good. These are really good. The idempotent completions are really harmless. And this proposition just says, okay, let's say you have two categories and a factor, and you can uniquely lift it to a factor between the idempotent completions. So not just it really just is, right? All properties we care about behave nicely with respect to idempotent closures completions. Right? So if you have a monoidal functor, then you get a monoidal functor between the idempotent completions. If you had a ba functor, then you get a ba functor between the idempotent completions, and not just any, and not just any, but basically there's exists the unique. So that's a pretty cool composition. So this says this is good. So this is my simple is really good. It's much better. It's much better behaved than the abelian. It's not as strong, right? You only have images for idempotence, but it's better behaved and you can apply it for everything, basically. Yeah, okay. There's not much to say about this lemma because I already said it. In the idempotent completion, you can actually write X as the image of, so you get this direct sum decomposition. Okay? That's what we wanted. Being idempotent complete is a property. And actually, additive functors are already the correct maps between additive categories. So you get the category of additive idempotent complete categories, which I denote by cut plus and this funny symbol here. So objects are additive idempotent complete categories. Remember, idempotent complete just means it's isomorphic to its idempotent completion or equivalent to its idempotent completion, but you can always kind of idempotent complete. And functors are just the additive functors which you already see. So this is pretty harmless, pretty nice. Okay, so this was the first part of the lecture. Idempotence, idempotent completions, and kind of a way to avoid going to the abelian world. The corresponding notion are colorings of diagrams, if you want, with idempotence to get idempotent completions, images of idempotence. Right. So this is up to this part. And now we are ready to discuss the question of this, the main question of this lecture. What is the right analog of algebras in categories? So what is the categorification of an algebra? So we want to use everything we have seen so far monoidal, pivotal, rigid, blah, 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 and we want to mix it with the linear algebra part, linear, additive, idempotent complete, whatever, a billion. Um, there will be some finiteness conditions. I don't want to go too much into details. It's written, I hope, reasonably carefully in the lecture notes, and you know, right, the lecture notes are in the description. So there will be some finiteness conditions, and usually if I write an F, then this means something like the category of finite, the categories of with some finiteness condition. The reason I don't want to go too much into details in this lecture with respect to finite conditions is there's still a lot to say, and it's a bit tricky to remember what finiteness conditions you need for what kind of um, structure, because what is going to happen now is kind of, well, it's just what always happens in category theory and in algebra. So there are just a lot of notions, and they're slightly different, and you need to write down carefully why they're slightly different, but they behave very similar. So for the first learning experience, it's much better to just, okay, there is a way to just think about it like this. There is a way to make this work. So let's ignore that and try to understand some examples, and then later we come back to the text and read carefully what are the exact properties. So in particular, there will be a lot of notions I'm going to throw at you. Don't worry too much. It's not super important. The main point, I will stress the main points. So there will be a lot of symbols, like there will be a W, there will be an M, there will be an L, whatever. Doesn't matter so much. Ignore it for now. And if you want to check it carefully. So the reason you need this is, again, I said again, in category theory and in algebra, you have you basically have counterexamples around any corner. So you have to extremely carefully write down what you want. Okay, and then it really, you want to make it as general as possible, but there are counterexamples around any corner. So you end up with zillions of different versions of basically the same idea. You have something locally finite, you have something finite, you have something weak, you have something strong, you have something pseudo, whatever. It's always the same idea. But you need to make those distinctions because not all theorems work in all setups. And I really want for now that you don't worry about that too much. Just keep in mind, I try to make this as explicit and correct and whatever as possible in the text, and that's fine. But for now, it just doesn't matter. It just doesn't matter if you're worried ever whether property X holds in the following setup, then just look it up. That's usually my strategy because at least I can't remember all that nonsense. I mean, it's important nonsense, but it's still hard to remember. I would rather like that you understand the idea that I'm trying to explain. Okay. And as I said, what I want is categorical analog of algebras. And I already have two competing notions running, and I don't want you to look too much at the various flavors of those two competing notions. I only want you to look at the two competing notions. And the two competing notions will be the following. I will be something that we'll call Fiat, and there will be something that I will call tensor or tensor category, whatever. And it works as follows. Okay. I have some ground ring field, whatever, and it's always the same. Okay, so it's already linear. And it looks very similar. So let's have a look at it. A category is called whatever real rule if it's rigid, S-linear, additive, idempotent complete. Okay, so that's the main point. Okay, and it has some finiteness conditions, and of course you want the monoidal product. So rigid, by the way, remember, implies monoidal. You want to be the monoidal product to be some reasonable thing. And for example, if it's pivotal, then I would drop the weak. If the identity, endomorphism of the identity would be the ground field, ground ring, then I would drop the multi. If it's finite, then I would drop the locally finite, and so on. But this is not so important, so let's ignore that for a while. Similarly here, it will exactly be the same. I will drop some weekly, blah, 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 blah. But let's ignore that and let's focus about on the differences. Because here we'll also have some finiteness conditions. I would ask the functor to be linear. So we have Fiat tensor, so far it looks the same. And I would ask everything like this. I would ask it to be rigid. I would ask it to be linear, but, and that's a crucial difference, I don't ask it to be additive. I don't ask it to be idempotent complete. I ask it to be abelian. Oh, that was really bad. I ask it to be abelian. Okay. So that's the difference. Here I ask additive and idempotent complete, and here I ask abelian. And that's a real difference. So what do we have? Let me say it again. Two notions. One of them is called Fiat. So this is the first one, and here's the second one. So first and second. I probably will call them first and second throughout the rest of the text, if I want to make this distinction. And they are just merging the concepts we have seen so far. They are rigid, which is monoidal and, well, to having duals. So remember, this was just you have a monoidal structure and you have basically duals, cups and caps. They are S-linear. No, that's, well, yeah, that's easy. And here I would assume that they are additive and idempotent complete. And here I would assume that they are abelian. And then there are some enrichments, as I said, which I'm going to ignore anyway. Or in the text, I'm not ignoring them, but at least in this lecture, I'm basically trying to sweep it a little bit under the rug because it's too confusing. You already have to remember that I have a difference between fiat and tensor, fiat and tensor, fiat and tensor, and the difference is additive or idempotent complete versus abelian, idempotent complete versus abelian. But both of them have dualities and tensor products. So here I also have dualities and tensor products. So let me just copy it down. Okay, so that's the difference. And if you think about it a little bit, okay, so now we have addition. So abelian categories also have addition. Remember that, right? In abelian categories, you have a direct sum. You just have more. They have cups and cap, but they have a monoidal product, so they already should categorify. So the Grothendieck ring will be a monoid with addition, so it will be kind of a ring. So both are kind of legit, absolutely valid categorifications, notions of categorifications of algebras or rings. And the real, as I said, the real difference is whether you want to consider the abelian world, which is a bit easier in practice, but doesn't appear in examples, or whether you, or it does appear, but it's rare, right? It's not as common as the other one. Or you want to be basically additive and idempotent complete, and you're in this setup, which is a bit more complicated in practice to prove theorems about it and so on. But more examples fit into slice one. Okay, so that was a mouthful. I hope it's kind of clear. So we have two notions. Difference is we kind of don't like abelian, or it's nice, but it's rare. So let's have a slightly weaker notion. It's not really weaker, a related notion, which we call fiat. But basically, both of them are just taking what we have seen so far, rigid and monoidal, and stick to them the notions we have seen in this lecture and in the last lecture, like additive and linear. Okay. The point is really this distinction. Like categories like vector spaces are tensor. Okay. Categories like Brouwer or Tepali-Lieb or Sum or whatever are usually not tensor. They're usually fiat. Because this abelian envelope is like a slightly bad notion. Okay. At least they are naturally fiat. Maybe that's how I should put it. Yeah, that's kind of the difference. Okay. So at one point you have tensor. It's everything is like vector spaces, and everything is more diagrammatic. Is more like in this fiat setup. Okay. And basically, how I want you to think about it is, remember that abelian was equivalent to mod A for some algebra A. And basically, those should be think of as generalization for some nice algebras, like bialgebras, which give us tensor product. Remember, Hopf algebras, which give us a duality, and some finite dimensional things which do those finiteness conditions, right? This is basically what it is. Okay? Mod A for some nice algebra. And above is kind of uh, the intrinsic definition of these categories. But I'm not talking about any algebra here or here. So the intrinsic definition. Let me give you a very explicit example, again, to say that those notions really differ. So maybe you remember my example of what it was, this one here. So characteristic 5, and I take Z mod 5. It's kind of a bad mixture, right? Z mod 5 and characteristic 5. And it's not so hard to see that this is actually pivotal. So it's rigid. So that's fine. You have cups and gaps. Well, that's no problem. And in the example before, I classified the indecomposable objects. This was Z1, Z2, Z3, Z4, and Z5. And they were given by those Jordan blocks of the corresponding lengths. Okay. And what you can do is actually, there's something funny. We'll see this in more generality, but taking the tensor product of any indecomposable with the one projective, so the Z5, the one projective indecomposable is actually the one projective, always spits out the projective itself, either just itself, or twice itself, or 3 times itself, or 4 times itself, or 5 times itself. And the projective is actually self-dual, which means that this thing, C prime, is actually a Fiat category, while C itself is a tensor category. Okay, so one finiteness conditions I forgot to mention, and that's kind of important. Well, it's written here, but I forgot to say it explicitly. For Fiat, we want a set of indecomposables to be finite. So this is Fiat. And for tensor, we want a set of simples to be finite. All right. So here you have, well, C prime. C is obviously a tensor category. I discussed the simples in it has only one simple. I discussed the simples in the previous example. It has 5 indecomposables, so it's still a Fiat category. But C is also itself a Fiat category because it has 5 indecomposables. And it kind of matters in what kind of distinction you want to take it. Whether, again, the difference is whether your focus is on idempotent, so on direct sum decompositions, and that means your focus is on indecomposables. That's a Fiat setup. Or your focus is on exact sequences. That's a abelian setup. And then your focus is on simples. So it's really, so this is above here. This is really, so Fiat cares about indecomposables, okay, and tensor cares about simples, and that's really the main distinction. And remember from last time that we had these two competing notions of what elements are, right? Elements could either be indecomposables, things that you can't decompose further, or simples, things without substructure. And since it's not quite clear which is the right notion anyway, it makes sense to have a distinction on this level as well. So you either like simples, then you would do a tensor, or you like indecomposables, then you would go Fiat. Anyway, good. So simples, indecomposables, simples versus indecomposables, tensor versus Fiat, tensor versus Fiat. That's what I would like to keep in mind. You get the corresponding categories by the usual yoga. Not so exciting. You just have to be sure what are the right notions of functors. So either it's additive rigid or it's exact rigid. And there are various words to add to it. It doesn't matter so much. Okay. That's the usual yoga. I hope that's by now familiar enough that I can kind of briefly go through it. So my finiteness conditions that I forgot to mention and I came back to it, in one sense are that I have a finite number of z's. These are the indecomposables. So just in numbers them by whatever, z1 to n. Or I have a finite number of l's, these were the simples. And I would also, let's say, just denote them by L1 to up to Ln, depending whether I'm in the Fiat setup or in the tensor setup. Yeah, I'm going to ignore this lemma. It basically says that everything behaves nicely with respect to the so the various structures like dualities and tensor product and addition and linearity, they work nicely together. The only takeaway message is the duality induces a bijection between the set of indecomposables. So some zi is sent to zi dual, which is some zj. It will be a permutation of the set of indecomposables. It won't be. I'm not saying zi dual is zi. I'm just saying it's a permutation on the set of indecomposables. Okay, so duality induces a permutation on the set of indecomposables. Okay. Okay. Let me skip those two. They're not so super important. Or let me just go briefly through them. So taking tensor products is an exact endofunctor. And this is kind of a funny thing. So projective times anything is projective in this setup. So the projectives kind of form a sink of the category. Whenever you have a projective, you can't go out of it. It's similar for injectives. You can't go out of it anymore. Tensor everything to it, and it will still be projective. It's just a nice fact. Rather, let me go to something better, or easier, whatever. Because you might wonder in what sense actually simples and indecomposables coincide. And this basically the right notion is a category to be semi-simple. Okay, a category is semi-simple if any object, so let's say additive, additive, whatever, every object can be decomposed into simples. It can always be decomposed into indecomposables, but I want them to be decomposable into simples. And then you call an object semi-simple, and of course you call a category semi-simple if all objects are semi-simple. So semi-simple categories. And again, the standard example you should keep in mind is vector spaces, graded vector spaces. Both of them are semi-simple. Okay, semi-simple. I don't really know what to do. SS semi-simple, semi-simple. And this funny example we had here is not semi-simple. And how do you see that? Well, we had those indecomposables, Z2, for instance. Z2 in this case is not isomorphic to, was it Z2? Yes, I think it was Z2. Z2 is not isomorphic to, there was only one simple. It's not isomorphic to any direct sum of this one simple. Okay, let me also skip this proposition. It's again not super exciting, but basically says that it shows lemma hold and you can control home spaces. So have a look at it if you read the lecture notes, but I'm running short on time, so let's move on. Semi-simple is important, so let's try to get a little bit more handle on semi-simple. And basically, this lemma is just to prove the next proposition, not so hard. And the next proposition, actually it's a lemma. To prove the next lemma is a category is semi-simple if and only if the simple objects are the projective objects. objects. Okay, simple equals projective, or dually, of course, simple equals injective. So kind of the projective object, if they're not simple, they measure how far away your category is from being semi-simple. Okay, so semi-simple. This is important. I don't know why I call it a lemma. But anyway, uh, it's semi-simple if and only if simple equals projective. Simple equals projective. Okay, this is semi-simple. If simple modules are projective, then things are semi-simple. In particular, you can prove, well, the following theorem. Any semi-simple category is abelian. It's actually surprising because they have a really different definition. Like abelian assumes something like an epimonic factorization and stuff. And semi-simple says something about decomposition of things into simple objects. But the point is, one of these propositions here actually gives you an epimonic factorization. And then it's not really hard to prove anymore that semi-simple is a special case of abelian. So semi-simple is kind of the case. So this theorem is basically saying semi-simple implies that basically that those two different notions, and this is kind of the only intersection where they are really the same. So for semi-simple categories, there is no distinction between elements, basically. So remember that you had this distinction between what you would call an element, a simple object, or a decomposable object. For semi-simple categories, it doesn't matter. Right? So the simple objects are the decomposable objects. So you're very happy. There is no distinction and everything's nice. So Fiat is tensor and whatever. The proof is not so hard. You just take, well, you can read it. It's not so bad. And actually, it's not quite trivial to see that all of these things here, those vec are abelian, but with this theorem, it's kind of trivial because they're basically by definition semi-simple. Okay. Problem is semi-simple categories are rare. So the classical Artin-Wedderburn theorem for algebras says that an algebra is semi-simple, meaning that its category of finite-dimensional modules is semi-simple. If and only if your algebra is some copy of vector spaces. So if and only if FD mod is equivalent to some number of copies of finite-dimensional vector spaces. And equivalently, semi-simple categories are rare. So a category is semi-simple if and only if it's equivalent as an abelian category to copies of finite-dimensional vector spaces. That's a little bit of a bummer. So semi-simple is such a nice notion, and then it turns out that basically only vector spaces are semi-simple, or any version of vector spaces. It's not so bad because this is not so, I mean, you would need to find this algebra, and this is usually not so easy to see. And usually your category in practice looks completely different than copies of vector spaces, but it will be copies of vector spaces if it's semi-simple. So kind of what this proposition is saying is, well, if you really, really care about semi-simple categories, then there are not so many of these. A little bit of a bummer. And a way to test whether a category is semi-simple is a so-called Muscus theorem. And it looks like this. A category is semi-simple if and only if the unit object is projective, or equivalently if it's injective. Okay, I want to do a little bit more diagrammatics. So I explain here where this actually comes from. So that's what I want to do. So for finite groups, what you actually can do is you can write down a certain idempotent in the group ring, which is just the sum over all group elements. So it's a finite group, so you can sum over all group elements. And that's basically an idempotent. The problem is if you square it, you see the group order. So M is the order of the group times itself. And the way to get rid of this is to divide by the order of the group. And then you get an idempotent, which splits off the identity from the group ring. Which basically means, if you think about it, that the identity is projective. It basically means um, that, which by this theorem means that the category is semi-simple. And that's why it's called Muscus theorem, because originally that's what he proved for group rings of finite groups. The only thing you observe here is that you want to be able to divide by m. So you better want that m, sorry, this was the wrong condition, that the characteristic of your field doesn't divide m. Right? And this is the classical Muscus theorem from uh, theory of finite groups. That's why I call it Muscus theorem. Okay, but I want to do a little bit more of diagrammatics. So let me wrap up here and let me completely ignore this lemma, which is basically saying that here you have an example of a semi-simple category. So endomorphism of the unit is a semi-simple category, or a semi-simple algebra, whatever. So what have you seen so far? Because now I want to do some diagrammatics. Okay, I started by explaining a slightly weaker notion of abelian, which was this idempotent completion, which then led us to two different definitions of categorifications of algebras. Either an additive one, which I call Fiat, where the focus is on indecomposables, or an abelian one, which I call tensor, where the focus is on simples. And the intersection point of those are the semi-simple categories, which are sadly really rare. Basically, they are copies of vector spaces. So basically, this is saying we really need to distinguish those two lines of definitions, of properties, of whatever. So we really need to distinguish indecomposables and simples all the time. This is just what it is. This is just what life gives you. Life gives you a choice, what you like to call the elements of your theory, and you want your periodic table of elements. But now you have a choice, as I said, either you like simples, things without substructure, you end up with abelian, or you like indecomposables, things that don't decompose further, you end up with something like Fiat, some additive version. And there's just no way around it. It's just what it is. And the only thing I want you to take away from the above discussion is, as I said, there is no way around. So let's distinguish it. And one of them lays a focus on indecomposables, and one of them lays a focus on simples. But let's do some more diagrammatics, right? This was a lot of algebra and abstract nonsense, and you need to read it anyway because there are a lot of little subscripts this week, weekly, locally finite versus finite, rigid versus pivotal, blah blah blah. But the main point is there are two different notions of elements, and we really need to distinguish them. There's just no way around. Only in the semi-simple case they agree, and semi-simple means we are working in vector spaces in one way or the other. Anyway, let's revise Tepali-Leap. Remember Tepali-Leap, or the Rumatella-Weil category, how I called it, because it originates in this paper by Rumatella and Weil, which I cite in this lecture notes if you want to take a look. Remember that this had those generators cap and cap, and that's basically it. And you just wrote down everything in terms of caps and caps, whatever. So diagrams like this, whatever, you get the point. Anyway, so let's do something funny with this category. So remember from the above discussion, so last lecture and what I did in the last, whatever, 1 hour, there's, you can always take it to be S linear, no problem. We can take a direct sum, no problem. We can do idempotent completion, no problem. So we get this category where you can now add diagrams, we can scale diagrams, we can, whatever, take idempotence. And this Temple-Leap is just a huge thing, and you want to make it finite to fit into some of those definitions above. And the trick to do it is to use the circle removal. Okay, so I assume that my ground field has some element that I call Q, and strictly speaking, actually, I assume that it has a square root. This is kind of one of these annoying things, but it doesn't really matter so much. You really need to do that because you want it to be braided. We will see that. Um, but basically, you need a Q. And what you do is you impose a relation on it. So whenever you see a circle in the diagram, you can pull it out and you add a factor, whatever, a factor like this in front of the diagram. Remember that we can scale diagrams. This is a legal element in our ground field because we assume Q is in our ground field, the ground ring, whatever. So whenever you see a circle, you remove it from the diagram and you pull it out as a scalar. This already makes the category much smaller, right? Now you can, the only things you can draw without creating scalars are things without closed components, right? So the red part here is fine, and you can always remove the green part by the circle removal. And I hope the name is kind of clear. We remove a circle. But actually, it's even better. It's actually a braided category by using these formulas. So you can express a crossing in terms of the generators. And this is called the Kaufman formula. And here you need whatever. A crossing is a linear combination. It's a two straight lines on the cup and the cap, and you throw in the Q's in the right way. And you get the following relation, which is clear if you write down this, and this is called the Kaufman's gain relation. Right? So this is already kind of doing kind of something of like topology, because in the end it will enable you to calculate something like a Jones polynomial. But for now, the main point is with those definitions. So Temperley-Lieb itself is very nice, diagrammatic, it's cobordisms, remember, but it's a bit too big. And the basic trick you do is you divide out circled components, you get a scalar, and you get a Brady. And that's exactly the statement. So this category is a braided Fiat category. It's not abelian. Same problem. Diagram categories are rarely abelian, but it's additive and idempotent complete, so it's Fiat. And it's pretty good. And you basically calculate it. With those definitions, it's not so hard. Just do it. Point is, now this is braided. This is great. And Fiat, which remember means that you have cups and caps and direct sums and whatever. So this is our first example of a category which has all properties we want. It's braided, it's linear, it's additive, it's rigid, it's everything. It's beautiful. And it's simple. It's really simple. Diagrams, and the only thing you do is you remove circles, basically. And that's it. So cup and cap diagrams, and the only thing you do is you remove circles. Yeah, so proof is not very hard. I'm going to ignore that anyway. So and it's actually room. So a calculation now shows this one, not very hard. So you can, if you have a kink, you can pull it straight, not quite. You get a scalar factor in front of it, but it doesn't really matter. What is it? Oh yeah, there you go. Something like that. Doesn't really matter. Some scalar factor in front of it, but you can basically pull kinks straight. So this is actually a ribbon category. So it's not just braided, but it's also ribbon, which in the end means the following funny thing. There's a well-defined quantum invariant. This is our first quantum invariant. Isn't that great? We're finally the first quantum invariant, where we just collect all the notions we had so far, and we get a quantum invariant. It goes from ribbon tangles to this Temperley-Lieb thing, and it does exactly what you think it does. It sends the generators on one side to the obvious generators on the other side. And that's, I mean, this is really good. And I call it the Rashid-Deakin derive. So RT, we'll see more RT. That's why I call it. So the RT, Rashid-Deakin derive idea, they call it the RT functor. And how does it work? So let me do this example. This example is really, really nice. Um, okay, so the value of a link, so here you have links, L, so links, for example, uh, and the link is just well, what do you think it is? Like an element from the monoidal unit to the monoidal unit. And the image under this functor ends in, well, a link is an element in the endomorphism ring of the monoidal unit in this R10 tangles, and the image of it lands in the corresponding thing in TL. But now, because you can remove internal components, the image is just an element in this ring. So let's say this is our ground ring. So it's an element in the ground ring. So up to taking square roots, it's an element. It's a polynomial in Q and Q inverse. That's what it is. And this polynomial is a Jones polynomial. And by construction, it's a quantum invariant. It's an invariant of the link. So for each link, you can write down a polynomial. So here I did it for this Hopf link. This is Hopf link. So I just write it down, blah, blah, blah. You do the calculation, and you end up with, um, with an invariant of the Hopf link. So no matter what kind of, this is really good. So no matter what kind of diagram I would use for the Hopf link, my invariant would always be the same. That's why it's called an invariant. It's always whatever it is, q plus q plus q inverse plus q to the minus 3. Right? So this is something you can just easily calculate for. I mean, for any link diagram, you can easily calculate this invariant. And you don't need to know anything except the diagrammatic rules from above. Whenever you see a crossing, you replace it by those two things. So here's a crossing. I replace it by this one and this one. I have the above crossing, and I keep track of the scalars. I replace it by this one and this one, and then shuffle it because, well, if I have two crossings and I replace two crossings by two expressions, then I get four expressions in total. You just sum them up. Count the number of components. Each component gives you a scalar like this one here, right? So here I see two components, I get two of those scalars. Here I see one component, I get one of those scalars. Here I see one component, I get one of these scalars, but those two combine in this thing. And this here I again see two components, so I see two of those scalars. Just add it up, and I end up with a polynomial in Q. So don't be confused that people like to call it Q. It's just a polynomial, or to be precise, a normal polynomial, because you take inverses as well. But it's a really, really easy process. And if you want to, well, if you would need to choose what you would like to understand from this lecture, then this is exactly this example. Do it yourself, do it for a different link, like a trefoil or whatever. And it's really beautiful. It's easy. It gives you an invariant from the machinery you have developed so far. It's just a functor from whatever ribbon tangles into uh, this Fiat category, this braided Fiat category we discussed. So we are there. We finally have a quantum invariant, and that's amazing, right? And you can do the same for something like a Brouwer category. That's what I'm discussing here. It gets more complicated because Brouwer is more complicated than Temperley-Lieb, but the idea is the same. You have circle removal. It's a bit more complicated, but it's the same. You have some scalar. You have Kaufman skein. So you have braiding, and you have a ribbon thing, so you can remove kings. So it's really the same idea. It's just a bit more complicated because it's Brouwer and not Temperley-Lieb anymore. But the statement is the same. It's a braided, it's a braided, this is great, and Fiat, this is great category. Same thing, and you get another quantum invariant. It's the same idea. It's really right. We have a machinery. As soon as we have those categories, we get all those quantum invariants. Same proposition. I just give it a different name, but it's the same proposition. You can do the same kind of calculations. Here we go, and you get a quantum invariant. Here you go, or whatever. Um, you get a polynomial invariant in this case. Here you go, of the Hopf-Link. It doesn't matter. Maybe this was too fast, but this doesn't matter. So remember, we have a machinery. As soon as we have a whatever braided Fiat category, you can run the machinery. You get a link invariant. That's the only thing you need to check. It's so amazing, right? So same strategy. Circle removal. You have some braiding relations. You get a braided Fiat category, which by this thing is actually what is it called? Ribbon as well. So you get this quantum invariant by the standard procedure, right? This is the point about the standard procedure. You don't need to think about it anymore. Just do it. You could calculate link invariance and so on. Yeah. So basically, we are done here. But let's just run through the rest. But basically, we're done. So we have constructed quantum invariance. We already applied our strategy. All you need to do is you need to write down, let's say, a braided Fiat category or a braided tensor category, and you depends a bit, right, whether you want simples or incomposables, and you can run the general machinery, which is really good. So I said again, and I think it's probably one of the exercises. Just try to understand those calculations. Then you're good. For this lecture, you're good, and you learn everything basically what is important. At least for the first one or whatever. So let me just wrap up. It won't be too bad anymore, but I kind of promised you that that we have categorifications of algebra. So that's what I should explain. I should explain Grothendieck groups and how they are algebras. So so what I'm going to do is I either take a C category, which is Fiat, or I take a D category, which is tensor, and I look at the corresponding Grothendieck groups, which is either defined by addition, the additive Grothendieck group, or by short exact sequences, the exact Grothendieck group. And what you can show is they are actually, well, the first thing that's easy, they are finite dimensional abelian groups. And actually, there's a multiplication structure, and everything is compatible. In particular, they are finite dimensional algebras. Okay, so Grothendieck, so collapsing morphisms, the Grothendieck construction of Fiat and tensor categories, depending which one you want. You do the short exact sequence version or you do the additive version, gives you the categorifications of finite dimensional algebras. Right? This is nice, and it of course gets better. Any functor between those defines you an algebra homomorphism on the Grothendieck group. Any functor between the D's defines an algebra homomorphism on the Grothendieck group. Right. So it's as good as it could be. Everything just works out. Let's not worry about those things too much here anymore, but basically the dimensions of the Grothendieck algebras, finite dimensional algebras, ranks, the dimensions, whatever, are invariants of C and D. So the first thing you kind of try to compute are those ranks. Okay. So let me run you through this example, and then we are basically done. We still need to do finite dimensional algebras and vector spaces, but that will be quick. So let me run you briefly through this example, where I have written down the multiplication table on the Grothendieck group in my favorite example. What was it? F5 Z mod 5. Remember, and in this case, I had something like 5 incomposables, and here's a multiplicative structure. of those five indecomposables, and this nails down the structure of the Grothendieck algebra. Um, yeah, so this is basically these are the structure constants of K0. Okay, so this nails down the algebra structure. This is a unit, as you can see from the table, right? The others are a bit more complicated, but not too bad. So the 5 one, the Z5, the projective one, is very easy. It just 2 times, 3 times, 4 times, or 5 times itself, depending what you multiply it. And actually, as a ring, this is isomorphic to Z. Okay. Okay. So the last thing won't be too bad anymore. We're almost done. Very quick. So what I've done here is I explained to you very briefly, of course, because I'm running very bad on time as usual. That either of those two notions, Fiat or tensor, if you take the additive or the exact Grothendieck group, you will get finite dimensional algebra. And the structure constants of the finite dimensional algebra, I've give you an example here for my favorite running example of f5 bar of z mod to 5. Um, so that's what it is. So finite dimensional. Okay. How can you actually find those examples, right? So the kind of the point is, okay, you have some machinery now. You only need braided, whatever, Fiat or tensor categories, and can write down. You can run the quantum invariant machinery. But how do you find them? Here's a way to do that. The main theorem. If you have a finite dimensional Hopf algebra, then finite dimensional modules operate as a tensor category. So Hopf algebra in the sense of the Hopf algebras, well, Hopf algebra as we discussed it before. So and basically Hopf algebras give you all the structures you need. It gives you rigidity, it gives you a tensor product, whatever. So Hopf algebras plays this crucial role in the construction of quantum invariants. That's why you always see them somewhere in the construction of quantum invariants. They're really like group-like. They're really the main source of examples of quantum invariants. Yeah, and here I have a little bit of a discussion, which I'm skipping now. I would rather like to, well, you can read it, of course. I basically explained in what sense Hopf algebras are group-like objects. Anyway, so group-like objects give you quantum invariants. That's basically what I'm explaining here. Anyway, I would really like you to do this example. This is great. So calculate those Leak invariants. In this case, so this is a trefoil. This is a trefoil. How do you spell trefoil? You spell trefoil like this, trefoil. And try to compute it in Temperley or in Brouwer or whatever. For those two versions of the trefoil, the left-handed and the right-handed trefoil. So these are two versions of the trefoil. So here's the left. I don't know which one is the left-handed. So two versions of the trefoil. One of them is the left-handed, and one of them is this mirror image, the right-handed version. And you can actually show using the quantum invariants that they're not equivalent, which is not completely obvious, because for other knots, that's actually not the case. The mirror image is equivalent to the knot. Also, you can't see it. There will be some crazy sequence of moves that makes them equivalent. So this is a very nice exercise. Otherwise, just have a look at the exercises. Maybe you like one of them, maybe not. But anyway, let me wrap up. So the main point we are seeing is actually the analog of this exercise. So we had this the machinery of quantum invariance, make it linear, make it additive, make it idempotent complete. That kind of comes for free. And if it's braided, then you already have an invariant of links. If it's ribbon, then you have an invariant of ribbons. Whatever. If it's whatever, then you have an invariant of whatever by basically by feeding your example in the machinery. And all I explained is today is basically how that works and how you want to be careful with distinguishing um, simple objects and indecomposable objects. So we have this notion of fiat versus tensor. But the main takeaway message is that we kind of have now a machinery to construct uh, quantum invariants. Just make everything linear, make everything additive, make everything idempotent complete. Hope that you have a braiding and you just feed it into a machine and you add a quantum invariant. And you can calculate polynomial. You can calculate everything explicitly because you're doing linear algebra. Anyway, I think that's all I have to say for today. And next time I will explain a little bit how to find and classify and construct whatever those Fiat tensor and tensor categories, because that's kind of the point that's missing, right? It basically tell you if you have a category of type X, Y, Z, then you get a quantum invariant, but the question is how to find categories of X, Y, Z. Okay, so that's it for today. I'm starting to waffle anyway, so hope to see you next time.